Hi there. So in today's lecture, we're going to be going over differentials. So we did cover this in the previous lecture, but there's just a few more things that we need to go through. So first of all, what is a differential? A differential, df, or the differential of the function f, is equal to df by dx times dx. Okay, so the way that we view this is df over here is a small change in the function, and dx, that's a small change in x. Okay, and df by dx, we know that that is the gradient. So if we take the gradient and multiply it by a small horizontal step, we get our small vertical step, which is df. Okay, so what we're going to do now is use this differential to make two approximations. Okay, so the first one is to find a linear approximation to a function at a given point. In other words, we're going to find the tangent line. Okay, because we know that given some function f, let's say maybe it looks like this, if we have the tangent line, sorry, let's draw that a bit neater. If we have the tangent line at a certain point P, then if we are slightly away from P, then the tangent line is still very close to the function. Okay, and that idea of it being very close is what we're going to use to develop this idea of a linear approximation. Okay, so linear for line, since we're using the tangent line. Okay, we can also get quadratic approximations and cubic approximations, but we will only see that again next year. Okay, so first, let's write our df as df by dx times dx. Okay, so this df and dx, those are infinitesimals, right? We take the limit and so on, but here we're going to replace that with finite changes. So instead of an infinitesimal df, we're going to replace this with a delta y. And then we're going to keep this df by dx, and this delta x, the dx, we're going to replace with a delta x. Now delta y, that's just the difference in two y values. So if we are at a point P, let's say given by x1, y1, then we can write this as y minus y1, where y1, that's the y value of the point P, and y is another y value along that line, is equal to df by dx, and then delta x, we're going to replace with x minus x1, similar to what we did with the y's. And this is just an equation for the tangent line, okay, like we saw previously. So we can write this as y minus y1 is equal to m, x minus x1, and that's just the equation of a straight line. Okay, so we can use this to find the tangent line, but now instead of just finding the tangent line, we're going to use this tangent line as an approximation to f near this point P. So this tangent line will be used as a linear approximation, since it's a line, as a linear approximation to f, or at and near the point P. Okay, so very close to P, it's a good approximation because the tangent line is quite close to the function. But as we move further away from P, we get a larger and larger discrepancy between the two graphs. Okay, and we can write down explicitly what this deviation is as the error in the approximation. That's going to be the absolute value of f of x minus our tangent line approximation y of x. So at point P, these two coincide, so the error is 0, but as we move further away from point P, the error is going to increase. Okay, so this is the error in the approximation. So error due to us approximating. Okay, so given a function f and a point x, we can calculate how bad this linear approximation is. Okay, so that is the first thing that we're going to look at with approximating. So using tangent lines as approximations. The second thing is approximating errors in measurements. So number 2, approximating errors in measurements. Okay, so what do I mean by that? So let's say we have a sphere of radius r. So just imagine here we've got ourselves a sphere and it has radius r. So we can calculate the volume V as 4/3 pi r cubed. Okay, so that's if we know the radius exactly. But what happens if we don't know the radius exactly? What happens if there's an error in our measurement of the radius? So an error in the measurement of the radius. Okay, so let's call this error delta r. Will induce an error, let's call that delta V, in the volume. Okay, so if we can't measure the radius exactly, then that means our volume will also be slightly off. So what we want to do is find out how the error in the volume is affected by this error in the radius. And to do that, we use, again, differentials. So we start with our volume equation, so V equals 4/3 pi r cubed. And from this, we calculate the differential. So that's going to be dV is going to be 4 pi r squared dr. Okay, so that's just taking the differential dV. Now we're going to replace these infinitesimal differentials with the finite difference. And that's going to be our error, or our approximation to the error. So here we have delta V is 4 pi r squared delta r. So if we know the radius that we measured and we know the error in our measurement, we can approximate the error in the measured volume. So this is the error or approximate error in measuring the volume. Okay, and it's a fairly good approximation under certain circumstances. So we're going to look at that now of how good this approximate error actually is. Okay, for this specific example. And then you can do the same thing for the other examples. Okay, before we get to that, just a quick little visual aid to see what we mean with this delta V. So let's say we've got ourselves that sphere. Okay, there's the center with radius r, and we have that error delta r. So let's say delta r is positive. Okay, it could be, so we say that this r might be a bit longer than we actually measured, so delta r. Okay, of course it could be a bit smaller, but let's say we have this r and we measure something smaller than it actually is. Okay, so here we've got a outer radius like that, So we've got this extended radius, r plus delta r, and that gives us a larger sphere. If we take the larger sphere volume minus the smaller sphere volume, we get this portion over here. Okay, so this in-between volume, so the volume outside the smaller sphere, but inside this larger sphere. Okay, so that volume over there, that is our delta V, or the error in volume. Okay, now this is just an approximation to that exact error. So let's find out what the exact error is and see how it relates to our approximate error. Okay, so exact delta V. This is just going to be something like VF minus VR. So VF, let's say that is the larger sphere, and VR, let's say that is the smaller sphere. Okay, so the larger one, that's going to be 4 over 3 pi r plus delta r cubed. Okay, because that has the larger radius where we add on the error. Okay, minus 4 over 3 pi r cubed. That's the one that we measure. So what we can do now is expand out that binomial, so the r plus delta r cubed, and then we can simplify some things. So this is going to be 4 over 3 pi. Expanding this out, we're going to get r cubed plus 3r squared delta r plus 3r delta r squared plus delta r cubed, and then we need to minus that smaller one, 4 over 3 pi r cubed. Okay, now two things will cancel here. So we have the 4 over 3 pi r cubed from that bracket minus 4 over 3 pi r cubed outside the bracket. So we can eliminate those. So this one and all of this, that's going to go, and then we can simplify the rest. So this will be 4, sorry, let's write that a bit bigger here. So that will be 4 pi r squared delta r for that first term, plus 4 pi r delta r squared for the second term, plus 4 over 3 pi delta r cubed. Okay, so each term has a larger power of delta r. So the first one is just delta r, the second one is delta r squared, and the third one is delta r cubed. Okay, now notice that if delta r is very small, so if it's very small, then delta r cubed will be smaller than delta r squared, which is smaller than delta r. So just think about an example. Let's say delta r is 1 over 10, then delta r squared is 1 over 100, that's even smaller, and delta r cubed is 1 over 1,000, that's even smaller than that. Okay, so the higher powers of delta r, those are going to be very small, and we can neglect those. So the term with delta r only will be the biggest, and then all the other ones will be smaller and smaller as we increase the power of delta r. So this is approximately 4 pi r squared delta r, and then plus those smaller terms that we're going to ignore. Okay, so this is the approximation we get by neglecting those higher powers, and we see that this matches up exactly with what we got with the differential case. So here we just took the differential and we've got our approximation, and we see it agrees very well with the exact error. So if we ignore those higher order terms, the exact error is approximately equal to the differential case. Okay, so the exact error, so that is the one with VF minus VI, is approximately equal to the error we get using differentials. Okay, but we see that using differentials is very quick. We just take the derivative, replace the differentials with deltas, and we get a good approximation. If we were to use the exact error, we see it requires quite a bit more working. Okay, and we end up with roughly the same answer anyway. So for our cases, we're going to use this approximate error using differentials. Okay, so that's going to be it for today. Please go through the tutorials. So there is one section on linearizing the function, so finding the tangent line and using it as a linear approximation. And then the rest of the tutorial is on this, finding approximate errors. So you're going to be given some function. We need to calculate the differential, replace the differential with the delta values, and then we use those delta values as approximate errors. Okay, so there's a couple word problems to go through with that. Okay, but we'll go through that properly on Thursday during the tutorial, and then do the MCQ. Okay, the first half of the MCQ, that will be on linearization, and then the second part of the MCQ will be on these approximate errors. Okay, so please try to go through that now in your own time. If you have any questions, please just email me and then I can get back to you. Okay, so I'll see you in the tutorial.